We're looking at the Eastern Cape September 2018 trial examination, and it's a photoelectric effect question, and they've given us a graph and we need to interpret the graph. This is a good question, not very difficult and easy to score marks, so pay careful attention. Different frequencies of light are shown onto a sodium metal plate, and the maximum kinetic energy of ejected electrons is determined each time. A graph of kinetic energy, maximum kinetic energy versus frequency for the metal is shown below. Define work function of a metal. And this is a definition that the work function is the minimum energy required by a metal to emit electrons. Write down the value of the work function of sodium metal. Now, what's important to notice is that this is a graph of kinetic energy on the y-axis versus frequency on the x-axis. And when we have a graph like this, it is your y-intercept that's going to always give you your work function. So we can say that our work function is 3,51 times 10 to the minus 19 joules. Be very careful of this 10 to the minus 19 joules, which is shown on the y-axis. And it's a positive answer because work function is energy, and we know that energy is a scalar, so direction is not taken into account. The same light photons are incident on zinc metal, so we can see the metal has changed. Initially we were using sodium and now they've changed it to zinc. How will the gradient of the graph for zinc metal compare to the gradient of the graph for sodium metal? So we need to firstly decide what is the gradient of this graph. So a tip for you, when you want to determine what is gradient we know is the change in the y-axis divided by change in x-axis. If I look at this graph, I can see that on the y-axis I have kinetic energy in joules, and on the x-axis I have frequency in hertz. So what we're going to do is we're going to place the units only here. We can say on the y-axis I have joules over hertz. And hertz means per second. So hertz can be rewritten as second to the negative 1. So that is a little bit of a trick there. So if I bring the second to the top, I would end up with joule second. And now I need to look for a physical quantity that has the units joule second, and that would be what the gradient represents. So if I look at the data sheet now, on the constant table, table 1, we can see that joule second does appear on this data sheet, and it is the unit for H, which is Planck's constant. So that would mean that the gradient of this graph represents Planck's constant. Okay, so continuing with the questions, they ask us to calculate the frequency FO indicated on the graph. And we can see from the graph that FO is the x-intercept of this graph. So there we have it, the threshold frequency. Sometimes they do give us the actual value here of the x-intercept, the threshold frequency, but in this question they didn't, so we need to calculate it. So we go to our data sheet and there's an equation that says that the work function is equal to HFO. This is an important equation which we usually use to find the work function. But we had already found the work function previously, and there's it. It is read off the graph, the y-intercept of the graph. So 3,51 times 10 to the minus 19. H is Planck's constant, which we get off the data sheet on the same table, table 1. And we know that it has a value of 6,63 times 10 to the negative 34. And FO we are trying to calculate. So when we put that into our calculator and solve, we get an answer of 5,29 times 10 to the 14 hertz. And that is the threshold frequency of this metal. And going on to the last question in this paper, and they ask us to calculate the wavelength of the incident photons that correspond to the frequency indicated on the graph above. So we know that we have a metal, and this metal has a specific work function, which we've calculated previously to be 3.51 times 10 to the minus 19. And we know that it has a specific threshold frequency of 5,29 times 10 to the 14. So it's very important to understand that the metal always has its own threshold frequency and work function. And then we have the light that's shining down on this metal. And this light consists of photons, individual particles or packets of energy. So light consists of photons, and we can calculate the energy of these photons by using the equation hc over lambda, or we can use the equation hf. So what's important to note is that this frequency here in the hf equation, this is to do with the light, whereas this frequency, the threshold frequency, is specific to the metal. So be very careful when you are listing your information, that you keep the information that's to do with the light separate from the information to do with the metal. So in our data sheet, there's a very important equation, and that equation says that the energy is equal to the work function plus the kinetic energy, the maximum kinetic energy. The E in this equation is specific to the light. So it's the energy of the light, right? So that would be here where we have some information. And WO is the work function of the metal. And kinetic energy would be the kinetic energy of the electrons that are emitted. And remember, we call the electrons that are emitted photoelectrons. So if I go to the information that I have, we know that the energy of the light is an unknown. In fact, they've asked us for the wavelength of the incident photons. They could have asked for the wavelength of the incident light as well. It would mean the same thing. So I can use the equation hc all over lambda. The work function we calculated it in the first question, 3.51 times 10 to the minus 19. And the kinetic energy we need to read off the graph, because the question said calculate the wavelength of the incident photons that correspond to frequency f indicated on the graph above. And now if we look at the graph again, we can see that here when the frequency is f, they've given us the kinetic energy to be 3,83. So 3,83 times 10 to the minus 19. Don't forget the 10 to the minus 19. H is a constant, 6,63 times 10 to the negative 34. C is also a constant, the speed of light, 3 times 10 to the 8. And we can see that lambda is going to be our only unknown in this equation. And when we put this into the calculator, we would get an answer for lambda of 2,71 times 10 to the negative 7 meters. And that would be the wavelength of the incident light or incident photons that correspond to the frequency f indicated on the graph above. I hope this video has been helpful to you. Please like and subscribe so that you don't miss any future videos. And share this video with as many of your friends as you can so that more people can benefit from these lessons.